On March 6, 1944, at 28,000 feet above Berlin, the 56th Fighter Group engaged German fighters in what would become the largest air battle yet witnessed over Europe. During this expansive combat, American Thunderbolt pilots encountered something that astonished their Luftwaffe adversaries. German fighters executed their usual escape maneuver, pulling into steep climbs to evade pursuit. For the past year, this tactic had been nearly flawless. The heavy P-47 Thunderbolt simply couldn't follow the climbing Focke-Wulf 190 or Messerschmitt 109. But on this March day, something had changed. American fighters remained locked onto German tails through climbs that should have been impossible. At altitudes nearing 28,000 feet, with both aircraft nearly stalling, Thunderbolt pilots opened fire. Black smoke streamed from damaged German fighters as pilots bailed out. By the mission's end, the 56th Fighter Group claimed 11 German aircraft destroyed without losing a single Thunderbolt. The transformation was complete. A modification to the Thunderbolt's propeller had eliminated the aircraft's critical weakness, fundamentally altering the tactical balance over Europe. This transformation began in the engineering departments of two American propeller manufacturers during the harsh winter of 1943, as bombers bled over Germany and fighter pilots reported German fighters escaping by climbing away. Engineers worked tirelessly to solve a deceptively simple problem. The Pratt & Whitney R2800 engine produced 2,000 horsepower, yet the P-47 Thunderbolt struggled to climb. The narrow-blade Curtiss electric propeller fitted to early production models couldn't convert that massive power into vertical performance. These blades were designed for high-speed cruising efficiency, optimized to cut through air with minimal drag above 350 meters. However, during climbs at low air speeds with the engine at full power, the narrow blades couldn't bite into enough air to efficiently convert horsepower into thrust. Engines screamed at maximum RPM, burning fuel and generating heat, but not providing enough lift. In January 1943, at the Republic Aviation Corporation headquarters in Farmingdale, Long Island, Alexander Cartelli reviewed combat reports from England with growing concern. German fighters dove through bomber formations, attacked, and then pulled into steep climbs to escape. Thunderbolts pursuing them couldn't keep up. Performance data was damning. Early P-47 models required lengthy climbs to reach combat altitudes, while the Focke-Wulf 190A and Messerschmitt 109G could reach those altitudes much more quickly. This performance gap resulted in American casualties. Pilots died in situations where better climbing performance could have saved them. Some Army Air Forces commanders questioned whether the P-47 should remain in frontline service. Cartelli understood the engineering problem. Propeller efficiency relies on matching the blade area to operating conditions. Narrow blade propellers worked well at high speeds, where thin blades minimized drag, but at low speeds during climbs. Blades needed more surface area to grab air and convert power into thrust. Increasing blade area seemed like the obvious solution, but it proved more complex. Every propeller design change affected the entire aircraft system. Incorrect blade shapes could create vibrations that might tear engines from their mounts. Improper weight distribution could generate harmonics, causing catastrophic structural failure. Incorrect torque characteristics could make aircraft uncontrollable during takeoff. Republic Aviation needed propellers with significantly more blade area that could integrate into existing aircraft without extensive modifications. Two companies competed to solve this problem: Curtiss-Wright, manufacturer of the original narrow-blade propeller, and Hamilton Standard, which produced propellers for several military aircraft. Both companies knew that the winning design would be manufactured in quantities exceeding 10,000 units, and more importantly, would determine survival rates for thousands of American pilots. Engineers at both companies worked through the winter of 1943, testing blade shapes in wind tunnels, calculating stress loads, and building prototype hubs and pitch control mechanisms. American pilots were dying while engineers refined blade chord lengths and twist angles. Hamilton Standard's engineering team developed a radical departure from conventional propeller design. Instead of thin, knife-like blades that sliced through the air, they proposed wide, paddle-shaped blades that grabbed air like oars pushing through water. The blade chord would increase dramatically, and the shape would be almost rectangular for much of its length before tapering near the tip. This design appeared crude to engineers trained in traditional aerodynamics, but wind tunnel tests revealed impressive results. The design generated significantly more thrust at low air speeds while sacrificing minimal top-end performance. Curtiss-Wright responded with their own wide blade design, maintaining a more traditional elliptical blade shape but significantly increasing the overall area. The Curtiss design featured blade cuffs at the root that smoothed airflow into the propeller hub and reduced vibration. Both designs represented massive improvements over the original narrow blades. Republic Aviation received prototype propellers from both manufacturers in April 1943. Testing began immediately at Republic's facility, and at Wright Field in Ohio, Republic's test pilots assessed both propeller designs in a systematic manner. Testing showed that both the Hamilton Standard and Curtiss propellers provided nearly identical performance improvements. Climb rates were dramatically better with either design. The Hamilton Standard offered slightly smoother operation due to hydraulic pitch control, while the Curtiss design integrated more effectively with existing aircraft systems and could be more easily retrofitted to P-47s already deployed overseas. Neither design was clearly superior in all aspects. The Army made a practical choice driven by manufacturing capabilities. Both propellers were approved for production. Hamilton Standard propellers would be used for new P-47s produced at Republic's Farmingdale facility, starting with the P-47 D-22 model. Curtiss paddleblade propellers would equip P-47s built at the Evansville, Indiana factory and be supplied as retrofit kits for earlier aircraft in England. This decision prioritized rapid deployment over a lengthy evaluation of theoretical superiority. The dual-source strategy would also complicate German intelligence efforts. Production began in June 1943. But manufacturing and testing delays meant the first operational aircraft didn't reach England until late December 1943. Throughout December, P-47s were flown to RAF Watersham, where mechanics retrofitted them with the new propellers. The 56th Fighter Group, flying from Boxted in Essex, completed the transition by early January 1944. Group Commander Lieutenant Colonel Hubert Zenker immediately recognized the tactical implications. The greatly improved climbing performance allowed his pilots to engage German fighters using vertical tactics that had been suicidal with the narrow blade propellers. Zenker organized intensive training through January 1944, developing new combat procedures specifically designed around the paddleblade Thunderbolt's enhanced climbing ability. He taught pilots to engage German fighters in climbing spirals, maneuvers that had previously left them vulnerable. He also developed techniques where pursuing P-47s would sharply climb if enemy fighters tried to escape, converting speed into altitude before diving back onto their targets with accumulated energy. With narrow blade props, such maneuvers would have left Thunderbolts at low speeds. With paddle blades, they became deadly offensive tactics. January 4, 1944, marked a significant milestone when the entire 56th Fighter Group flew its first mission with all aircraft equipped with paddle blade propellers. Pilots immediately noticed the difference. Aircraft climbed with an eagerness that seemed impossible for 7-ton fighters. Energy retention in vertical maneuvers dramatically improved. Thunderbolts could now follow German fighters into climbing escape maneuvers without losing position. The real test came when they encountered the Luftwaffe over Germany. The combat debut occurred during escort missions in late January and early February 1944. American fighters encountered situations where German pilots executed standard escape tactics, only to find pursuing Thunderbolts matching their climbs. Initially, German pilots assumed they were facing a new American fighter. When intelligence officers examined gun camera footage showing standard P-47 Thunderbolts achieving this performance, confusion spread among Luftwaffe units. How could the same aircraft they had successfully evaded for months suddenly match their climbing abilities? March 6, 1944, provided dramatic confirmation. Lieutenant Colonel Zemper led 48 Thunderbolts on a bomber escort mission to Brunswick, routing over Berlin. Luftwaffe controllers dispatched more than 80 Messerschmitt 109s and Focke-Wulf 190s to intercept the incoming bombers. As the bombers approached at 24,000 feet, German fighters attacked using their standard tactics, diving through the formations before pulling into steep climbs to escape. Across the battle, Thunderbolt pilots matched German fighters in vertical combat for the first time. Captain Robert Johnson, Lieutenant Walker Mahurin, and other 56th Fighter Group pilots engaged German fighters in climbing encounters and destroyed them at high altitudes. The group claimed 11 victories without losing a single Thunderbolt. More importantly, not a single bomber in their formation was shot down. German pilots returning from the Brunswick mission reported unsettling developments. American Thunderbolts were climbing with them. Multiple pilots insisted they must have encountered a new fighter type. When shown gun camera footage showing standard P-47s achieving the same performance, confusion deepened. Luftwaffe technical intelligence needed to figure out what had changed. The first clue came from wreckage analysis in early February. A shot-down P-47D-23 was transported to the Luftwaffe test facility at Recline. Engineers examining the aircraft immediately noticed the propeller. The blades were much wider than those on previously captured Thunderbolts. The technical intelligence report described the new design, but initially failed to recognize its significance, concluding that the modification likely improved takeoff performance rather than combat capability. This misunderstanding cost the Luftwaffe valuable time. By the end of February 1944, more P-47 groups transitioned to paddleblade propellers. The 4th Fighter Group received theirs in early February, and the 78th Fighter Group completed their transition by mid-February. By the end of the month, 6 of the 8 Thunderbolt groups in England flew aircraft equipped with paddleblade propellers. Each group immediately saw improved combat performance. Effectiveness soared as German fighter losses increased, with Luftwaffe pilots realizing that their standard escape tactics no longer worked. On February 21, 1944, Jagdgeschwader 26 lost 7 Focke-Wulf 190s in a single engagement with the 56th Fighter Group. Unit Commander Major Klaus Mitos filed an after-action report expressing frustration. His pilots had engaged according to established doctrine, disengaging through climbing attacks when pressed. However, every pilot who attempted this maneuver was shot down. Mitos requested immediate clarification on whether the Americans had introduced a new fighter type and whether existing tactical doctrines still applied. Luftwaffe intelligence had no satisfactory answers. German understanding improved through observation and wreckage analysis. By March 1944, Luftwaffe intelligence recognized that American engineers had modified the Thunderbolt's propeller to improve thrust at low airspeeds, particularly during climbs. Reports circulated warning that American fighters could now contest vertical combat, recommending engagement only when holding a clear energy advantage and disengaging through level, high-speed flight instead of climbing to escape. However, changing tactical doctrine across hundreds of fighter squadrons proved impossible. Pilots who had survived by climbing away for the past year could not instantly reprogram their survival instincts. The transformation became undeniable during Big Week, the massive bombing campaign against German aircraft production facilities in late February 1944. From February 20th to 25th, the 8th Air Force launched over 3,800 bomber sorties, escorted by more than 3,600 fighter sorties. The vast majority of American fighters were paddle-blade-equipped P-47s. The Luftwaffe launched over 2,000 sorties in defense. Germans lost approximately 355 fighters destroyed, with another 100 damaged beyond repair. American fighter losses totaled just 28 aircraft. The exchange ratio had shifted dramatically. Thunderbolt pilots discovered that paddleblade propellers created opportunities beyond simple climb performance. Increased thrust at low speeds improved acceleration out of dives, allowing Thunderbolts to build energy faster after high-speed attacks. Pilots could execute dive and climb attacks repeatedly, maintaining the initiative throughout extended engagements. The improved thrust also enhanced turning performance at slower speeds. While Thunderbolts still could not outturn Messerschmitt 109s or Focke-Wulf 190s in flat horizontal turns, they could maintain sufficient energy in climbing turns to prevent German fighters from gaining an angular advantage. Major Francis Gabreski, commanding the 61st Fighter Squadron within the 56th Fighter Group, became the leading proponent of what pilots called the climbing spiral. Gabreski would engage a German fighter at co-altitude, typically around 24,000 feet. Rather than attempting to outturn the enemy horizontally, he would maintain speed and pull into a climbing turn. German pilots, seeing the Thunderbolt climb, often followed, expecting the American fighter to lose energy and become vulnerable. But with paddleblade propellers, P-47s maintained their climb rate even while turning. Gabreski would spiral upward through 2 or 3 full circles, gradually reducing the German fighter's energy state until the enemy stalled or was forced to break off. At that moment, with the German fighter at low speed and high altitude, Gabreski would reverse, dive onto the target, and open fire from a position where the enemy had no escape route. Gabreski ultimately claimed 28 aerial victories, flying P-47 Thunderbolts, making him the leading American ace in Europe, flying a single aircraft type. Nearly all these victories came after his squadron transitioned to paddleblade propellers. In post-war interviews, Gabreski consistently credited the new propeller as the single most important factor in the P-47's transformation. The modification required minimal changes to pilot training. Aircraft simply did what pilots wanted, maintaining energy in situations where narrow-blade-equipped Thunderbolts would have failed. The paddleblade program showcased American industrial capability operating efficiently. From initial concept to widespread deployment took only 9 months. 2 companies designed, tested, and began manufacturing 2 different propeller designs. Republic Aviation modified production lines at 2 factories. The Army Air Forces developed new maintenance procedures, trained mechanics, and shipped thousands of propellers across the Atlantic. No single aspect was revolutionary, but the achievement lay in the speed and scale of implementation. The United States identified a critical deficiency and corrected it faster than Germany could develop countermeasures. German aircraft designers had the technical knowledge to create similar improvements. Both Messerschmitt and Focke-Wulf employed experienced propeller engineers who understood the theoretical benefits of increased blade area. However, the German war economy in 1944 could not support rapid modification programs. German aircraft production operated at maximum capacity, focused on producing existing designs in sufficient quantities to replace combat losses. Introducing new propeller designs would require retooling production lines, recertifying aircraft performance, updating maintenance manuals, and training mechanics. Production disruptions would cost thousands of fighters, and Germany desperately needed every aircraft. Germans were trapped by their strategic situation. They needed to American improvements in aircraft development outpaced German efforts, which were hindered by production constraints. While Germany could not afford the production disruption required to match American advancements, this revealed a key difference in the approaches of the 2 nations. American designers prioritized quick, effective solutions, accepting designs that were good enough for immediate implementation. The paddleblade propeller, while aerodynamically less efficient than more advanced designs, solved the pressing problem of climb performance. It generated more drag than narrower blades at high speeds and was heavier, requiring reinforced hubs and pitch control mechanisms. However, it addressed the immediate tactical need without the lengthy development process that would have optimized every detail. In contrast, German designers often pursued theoretical perfection, focusing on advanced variable pitch systems that, in theory, would outperform the American paddleblades. However, these advanced systems remained mostly on paper, with few reaching operational service in meaningful numbers. By March 1944, the paddleblade Thunderbolt had become the standard American escort fighter in Europe. It was no longer seen as a compromised platform awaiting replacement by the longer-range P-51 Mustangs. Instead, the Thunderbolt had evolved into a formidable air superiority fighter, dominating German opponents in most combat scenarios. The psychological impact was substantial. American bomber crews, who had previously watched helplessly as German fighters climbed away throughout 1943, now saw enemy fighters chased down and destroyed in climbing combat. German pilots, already demoralized by the growing numerical superiority of American forces, faced a tactical environment where their advantages were neutralized. The Focke-Wulf 190, designed to surpass the Thunderbolt in nearly every performance category, found itself matched or even outperformed in the one area where it had maintained clear superiority. The Messerschmitt 109 could no longer rely on vertical maneuvers to escape combat. German fighter losses climbed steadily through the spring of 1944, with many veteran pilots who had survived years of combat being shot down by Thunderbolts. They thought they had successfully evaded. The full impact became evident during the preparation for D-Day. Throughout May 1944, American fighters conducted intensive operations to achieve air superiority over France. Thunderbolts ranged across northern France, attacking German airfields, destroying aircraft on the ground, and engaging any Luftwaffe fighters that attempted to interfere. Paddleblade-equipped P-47s proved especially effective in these fighter sweeps. When German fighters scrambled to intercept, they typically climbed from lower altitudes to reach American fighters operating at 20,000 to 25,000 feet. Thunderbolts could now dive on these climbing German fighters, attack, and then climb away before the Germans could retaliate. On June 6, 1944, as Allied forces stormed the Normandy beaches, Thunderbolts provided air cover throughout the day. German fighters attempting to attack the invasion fleet or support German ground forces were consistently intercepted and destroyed by paddleblade-equipped P-47s. The Luftwaffe managed fewer than 100 sorties over the invasion beaches during the critical first 24 hours. In contrast, American fighters flew more than 8,700 sorties during the same period. This overwhelming superiority was possible because American fighters achieved kill ratios of 4:1 or better. The paddleblade propeller, by eliminating the Thunderbolt's primary weakness, directly contributed to the air superiority that made the invasion possible. Statistical evidence supported what pilots experienced. In the first quarter of 1944, before paddleblade propellers became widespread, American fighters in Europe achieved an overall kill ratio of approximately 1.8:1 against German fighters. By the second quarter of 1944, with most American fighters equipped with paddleblades, the kill ratio improved to 3.2:1. By the third quarter, it reached 4.61. These improvements cannot be attributed solely to propeller modification. American numerical superiority was increasing, pilot training was improving, and Germany was fielding inexperienced pilots to replace mounting losses. But combat reports make it clear that improved climbing performance played a significant role in these victories. The Curtiss Electric C542S paddleblade propeller, the most widely used variant, featured 4 blades with a 13-foot diameter. Each blade had significantly increased area compared to narrow blade predecessors. This substantial increase translated into dramatically improved thrust at low air speeds. The Hamilton standard hydrostatic paddle blade fitted to later production P-47s offered similar performance with operational advantages. The Hamilton standard design used hydraulic pitch control, which was simpler and more reliable than the Curtiss electric system. Total blade area was nearly identical, and combat performance was indistinguishable. The manufacturing effort required to equip the P-47 fleet demonstrated American industrial capacity at scale. Both Curtiss-Wright and Hamilton Standard produced thousands of propeller assemblies between June 1943 and December 1944. Each assembly consisted of 4 blades, a hub assembly, a pitch control mechanism, and mounting hardware. The blades were forged from aluminum alloy, machined to precise airfoil shapes, and heat-treated for maximum strength. Each blade required approximately 14 hours of manufacturing time. Machine time, excluding raw material preparation and finishing operations, was significant in the production of the propellers. Each assembly weighed approximately 650 lbs and needed careful handling to prevent damage during shipping. Propellers were packed in wooden crates with protective bracing and shipped across the Atlantic on cargo vessels, with voyages typically taking about 2 weeks. Upon arrival, propellers were sent to air depot facilities, where mechanics installed them on the aircraft. The installation process took approximately 16 hours per aircraft, which included the removal of old propellers, installation of the new ones, rigging pitch control systems, and conducting ground tests. Between January and June 1944, air depot mechanics in England retrofitted over 1,000 Thunderbolts while maintaining the operational readiness of frontline fighter groups. The tactical evolution of paddleblade Thunderbolt operations continued. Throughout the summer and fall of 1944, pilots developed more sophisticated techniques to exploit the improved climbing performance. One particularly effective tactic was the vertical scissors, where 2 Thunderbolts would engage a German fighter in a climbing dogfight. As the enemy aircraft climbed to escape one P-47, the second would position itself to attack once the German fighter lost energy and could no longer climb effectively. The German pilot was faced with an impossible choice: continue climbing until stalling, making him an easy target for the trailing Thunderbolt, or roll out to maintain airspeed, allowing the lead Thunderbolt to execute a diving attack. Another significant development was the use of paddleblade Thunderbolts for low-altitude ground attack missions. The increased thrust at low speeds allowed heavily loaded P-47s to maintain speed and maneuverability even when carrying 2,500 lbs of bombs or rockets. Pilots attacking German ground targets could enter attack dives from lower altitudes, reducing exposure time to anti-aircraft fire. After delivering their ordnance, paddleblade-equipped Thunderbolts could climb away from target areas more rapidly, again reducing vulnerability. Between April and September 1944, Thunderbolts flew over 88,000 ground attack sorties, suffering approximately 820 losses to all causes, a loss rate of less than 1%. The versatility of paddleblade Thunderbolts allowed them to remain in frontline service, even as longer-ranged P-51 Mustangs became available. Many fighter groups chose to retain Thunderbolts specifically because improved performance made them exceptionally effective in multiple roles. The 56th Fighter Group, commanded by Colonel Hubert Zanker and later Colonel David Schilling, flew Thunderbolts exclusively throughout the entire war. Despite opportunities to transition to Mustangs, the group's pilots believed the rugged construction and 8-gun armament, combined with the excellent climbing performance provided by paddleblade propellers, made it superior to the Mustang for their operations. German fighter pilots who survived the war consistently mentioned the paddleblade Thunderbolt as one of the most capable American fighters they faced. Major Günther Rall, who survived with 275 victories, noted in post-war interviews that the improved Thunderbolts were far more dangerous than earlier versions. He stated that German pilots had to treat paddleblade Thunderbolts with the same respect they afforded the P-51 Mustangs. Recognizing that the American fighter could match German performance in most combat situations, the engineering Lessons learned from the program influenced American aircraft development throughout the remainder of the war. The rapid development and deployment of the paddleblade propeller demonstrated that incremental improvements to existing aircraft could often provide better value than developing entirely new types. The P-47 itself benefited from continued improvements beyond the propeller modification. Water methanol injection systems increased engine power to 2,535 horsepower for short periods. When combined with paddleblade propellers and improved thrust characteristics, this further enhanced performance. The P-47M, introduced in late 1944, incorporated both modifications and could climb rapidly, matching or exceeding the climbing performance of any German fighter. The financial investment required to develop and deploy paddleblade propellers was modest compared to the operational benefits achieved. Development costs for both Curtiss and Hamilton standard propellers, including wind tunnel testing, prototype construction, and flight testing, totaled approximately $3 million. By comparison, developing an entirely new fighter aircraft would have cost at least $100 million and taken 2 to 3 years to reach operational service. The paddleblade propeller represented exactly the kind of cost-effective improvement that made American air power difficult to match. Paddleblade propellers also highlighted the importance of feedback loops between combat operations and aircraft development. Problems with narrow-blade propellers were identified by frontline pilots who filed after-action reports describing German fighters escaping through climbing maneuvers. These reports were filtered through intelligence systems, reaching engineers who could diagnose the root causes and develop solutions. This feedback loop operated quickly, with problems identified in combat, leading to engineering solutions within months. German forces had similar challenges, but feedback systems in theory, though acknowledged by the Germans, became increasingly disrupted by the chaos of Germany's deteriorating strategic position. The strategic impact of the Thunderbolt's transformation extended beyond direct air combat. Achieving air superiority over Europe, to which the improved Thunderbolts contributed significantly, allowed Allied ground forces to advance with minimal interference from German air power. During the breakout from Normandy in August 1944, American ground forces advanced under the umbrella of air superiority, largely maintained by Thunderbolts. German ground forces attempting to retreat or reposition found themselves under constant attack from Allied fighters. The improved climbing performance meant that German fighters attempting to interfere with ground attack missions could be quickly intercepted and destroyed by escorting P-47s. The final major air combat involving large numbers of paddleblade Thunderbolts occurred during the Battle of the Bulge in December 1944 and January 1945, when German ground forces launched a surprise offensive through the Ardennes. Bad weather initially prevented effective air operations. However, when the weather cleared on December 23rd, Allied air forces launched massive attacks against German ground forces and supply lines. Paddleblade-equipped Thunderbolts flew hundreds of sorties daily, attacking German armor, trucks, and artillery positions. Luftwaffe fighters attempted to interfere, but were consistently driven off by escorting P-47s. By February 1945, organized Luftwaffe resistance over Western Europe had effectively ceased, with German fighter units being withdrawn to defend the homeland against an increasing strategic bombing campaign. Paddleblade Thunderbolts played a significant role in achieving this air superiority, though their contribution was often overshadowed by the more glamorous reputation of the P-51 Mustangs. Military historians analyzing the air war have sometimes downplayed the Thunderbolt's importance, noting that P-51s achieved more aerial victories and flew deeper into Germany. However, this overlooks the crucial point that the Thunderbolt's transformation through the paddleblade propeller modification came at a time when German fighter forces still represented formidable threats. Between January and December 1944, Thunderbolts were credited with destroying 382 German aircraft in aerial combat, while losing 824 P-47s to all causes in the European theatre. This represented an overall kill ratio of 3.7.1, comparable to or better than other American fighter types during the same period. More importantly, the Thunderbolt's transformation. From a mediocre climber to a capable vertical fighter occurred during a period when such capabilities were most urgently needed. The post-war fate of paddleblade Thunderbolts demonstrates how quickly wartime innovations can be forgotten. As jet fighters entered service, propeller-driven P-47s quickly became obsolete. Most surviving Thunderbolts were scrapped or sold to foreign air forces. The technical achievements that made paddleblade Thunderbolts effective fighters were eclipsed by the revolutionary capabilities of jet propulsion. Few pilots who flew the improved Thunderbolts in combat went on to positions where they could ensure the proper historical recognition of the propeller modification. Yet the paddleblade propellers represent a fundamentally important type of military innovation deserving greater recognition. It wasn't a revolutionary breakthrough that changed the fundamental nature of air combat, but an evolutionary improvement that took an existing platform and eliminated its most critical weakness through relatively simple engineering. This type of innovation, while less dramatic than the development of revolutionary new technologies, was often more immediately impactful and characterized much of American military success during World War II. The ability to identify problems, develop practical solutions, implement them rapidly, and deploy them at scale gave American forces decisive advantages. The engineering principles underlying paddleblade propellers remain relevant to modern military aviation, even with the transition to jet propulsion. The fundamental insight that blade area must be optimized for intended operating conditions, rather than for theoretical maximum efficiency, applies to turbine blade design, helicopter rotor design, and unmanned aerial vehicle propulsion systems. Military engineers still face the challenge of balancing multiple performance requirements across different flight regimes. The German perspective on paddleblade Thunderbolts provides sobering lessons about the consequences of industrial and strategic weakness. German engineers understood propeller theory just as well as their American counterparts. German aircraft factories were capable of producing improved propellers had they been given the resources and opportunity. But Germany's deteriorating strategic position, resource shortages, and increasingly disrupted industrial base made rapid improvement programs impossible. Paddleblade Thunderbolts succeeded not because American engineers were more skilled, but because American industry could support rapid innovation while German industry could not. Wars are not won by single wonder weapons, brilliant strategies, or revolutionary technologies. They are won by the accumulated weight of thousands of incremental improvements, each addressing specific problems, each implemented efficiently, and each contributing to overall superiority. The paddleblade propeller was one such improvement among many, but it came at a critical moment when German forces were still capable of contesting Allied air superiority. By eliminating the Thunderbolt's primary weakness, the modification helped establish air dominance that made the invasion of Europe possible and accelerated Germany's defeat. This achievement, born from the mundane work of propeller engineers rather than the dramatic exploits of fighter pilots, deserves recognition as one of the decisive technological contributions to Allied victory in Europe.